Hi, good afternoon to all of you. I'll share the slide. Uh, I hope you're able to see the slide. Please confirm that.
Yes, sir. Yes, sir.
Okay, thank you. Okay, so we'll get started. Please recall that we have been looking at the non-dimensional form of the governing equations. I'll just quickly rewind what we have discussed. We are considering steady inviscid flow, steady inviscid hypersonic flow. So we are considering the appropriate governing equations, that is the set of equations without the viscous force terms, and of course heat transfer. So when we have, without heat source terms. So when we have the steady inviscid forms, what we did next was try to non-dimensionalize the equation. That is, we tried to replace the dimensional parameters like pressure, density, etc. by an appropriate set of non-dimensional parameters. For example, I'll just go to that. We non-dimensionalized the velocity by the free stream value. So instead of v, we wrote v by v infinity. Similarly, rho as rho by rho infinity, p by rho infinity squared, rho infinity v infinity squared for pressure, and temperature was normalized by T by v squared by Cp. So by and similarly the the dimension of the body was x and y were non-dimensionalized by the streamwise distance, streamwise length, x by L, v by L, y by L, etc. So that is one thing we did. So we had a set of non-dimensionalized governing equations for the problem. The next thing that we did was we looked at the boundary conditions. That is, we considered the domain boundaries. We are interested in, keep in mind, we are interested in calculating the pressure distribution on the body. So the boundaries of the domain of interest and include the flow near the body, which is the flow just after the shock, and the body surface itself. So the boundary conditions pertain to the conditions along the, or rather, just downstream of the shock and on the surface of the body, because they are the boundaries of the domain. Now we saw that we can non-dimensionalize the conditions. That is, we can express pressure ratios, density ratios, velocity ratios using the all using the shock relations. And also on the body, we saw that the velocity components, etc., can be non-dimensionalized appropriately. We also see that the shock conditions, when we extend them to the hypersonic limit, they all become independent of Mach number. So non-dimensionalized pressure, for example, becomes 2 sine squared beta by gamma plus 1. Non-dimensionalized density becomes gamma plus 1 by gamma minus, etc. All of them happen to be independent of Mach numbers, which means that on the shock side, we can express all the boundary conditions for the respective non-dimensional variables, that is P2 bar, rho 2 bar, U2 bar, etc. For all the non-dimensional variables, the boundary conditions can be expressed as non-dimensional, as independent of Mach number. And similarly on the wall also, that we have seen, we looked at the velocity contours, etc. Sorry, the tangential condition of velocity, or rather, yeah, that is the lack of normal component, because we are considering velocity, we are, because we are considering inviscid flow, which means that the velocity at the wall, or the boundary conditions along the wall, can also be expressed as independent of Mach number. Now we come to the conclusions based on this. Just starting from the box, the first box, I'll just try to indicate that here. The steps that we followed was, governing equations are expressed, and in terms of the way, in terms of the parameters that we have defined, they are all independent of free stream Mach number m infinity. That is, we, in the boundary conditions, when we non-dimensionalize them using these parameters, we see that the resulting set of boundary conditions do not have Mach number in that, or they are all independent of Mach number. One. Second is, the boundary conditions at the wall as well as near the shock are independent of Mach number when Mach number tends to infinity. That is for high hypersonic kind of applications. So that is unique. That is, when the flow Mach number tends to high infinity, the shock relations become independent of Mach number. Now let's look at these 1, 2, 3 together. What we are saying is that we have a set of non-dimensional boundary conditions, we have a set of non-dimensional equations, and all of them are independent of Mach number, which means that their solution means solution for the variables like which are expressed in terms of non-dimensional parameters like p bar, rho bar, v bar, etc. So the solutions also will have to be non-independent of Mach number. I hope that is clear. That is, the boundary conditions are independent of Mach number. Sorry, the equations are independent of Mach number. Their boundary conditions are independent of Mach number, and which means that if we were to solve those equations subject to these boundary conditions, the resulting non-dimensional parameters or non-dimensional variables or the solution will also be independent of Mach number. Now, this observation leads to the concept of Mach number independence in hypersonic flow. That is, what it says is that, or what it helps us to conclude is that a combination of, or rather, a formulation of the boundary, the equations using the non-dimensional parameters, and if we solve for those non-dimensional parameters, the result will be independent of Mach numbers, which in turn can be generalized as, in hypersonic flow, the non-dimensional parameters, and so actually, say by P, what we mean by that is v by v infinity, rho by rho infinity, and p by rho v infinity squared, etc., are all independent of Mach number. What, which in turn means that, say, p by, for example, if I take the non-dimensional parameter pressure, p bar, which is defined as p by rho infinity v infinity squared, I can express the pressure coefficient in terms of that. And similarly, I can have the non-dimensional aerodynamic coefficients L and D, the lift, CL and CD, which are all non-dimensional, and they are all dependent on the pressure distribution. And I can express all of them using the non-dimensional pressure variable, which means that all the non-dimensional aerodynamic coefficients can also be independent of Mach number. Now, this is an important observation. What it tends to tell us is that in hypersonic flow, if you are able to calculate, if you are able to take, experimentally determined values at a lower Mach number, say 5, Mach 5, Mach 6, etc., you can extend their validity to high Mach numbers also in terms of the non-dimensional parameters. So, which means aerodynamic coefficients which are non-dimensional, they can be considered to be independent of Mach number. This is a quite handy information. Now I'll tell you why it is helpful, but please keep in mind that this involves a lot of assumptions and approximations, etc. So actually this is not the end of the hypersonic problem. It's not, I'm not trying to say that if you can calculate aerodynamic coefficients at low Mach numbers, if you can determine them experimentally at lower Mach numbers, you can use everywhere. No, you still lose a lot of accuracy and etc. because we are when we approximate the hypersonic limit, we are assuming the Mach number to be infinity, etc., which is not the case. So there is a finite amount of compromise on the accuracy, but for initial estimation, it's safe to consider that many of these aerodynamic coefficients can be considered to be independent of Mach number. Okay, I'll try to. Okay, I'll pause here for a minute. If you have any doubts, please ask now. No question. So I assume that the concept is clear. Now I'll try to explain this further in terms of what people have reported in terms of experimental confirmation of this. Now again, confirmation of sorts with all those qualifiers. Look at the curves there. Look at the data that is plotted here. It has two bodies, one a cone cylinder and the other a sphere. I'll try to point out the curves. Sorry, yeah. Now you can see that there are two graphs which are shown, one for a sphere and the other for a cone cylinder. That is a shape which is shown there. That is with an included angle of 60. The graphs that you see are CD versus Mach number. That is, on the y-axis, CD is plotted. On the x-axis, it's Mach number. If let's just look at one of them. I'm just trying to show one of the top one actually. Let's try to understand what is the message carried by that particular graph. You see that as Mach number increases from the from the ratio 0 to 2, from the range 0 to 2, the CD value increases. CD, what is CD? The non-dimensional drag force. So the coefficient of drag increases with Mach number and sort of reaches a maximum value and then reduces a little bit. And then these are experimental values again. And then they tend to be almost constant. See, that is, these are experimental values, which means that say after 4 or 5, after 4.5, the CD value, that is the non-dimensional drag coefficient, almost tends to be constant with Mach number. Okay, that is independent of Mach number. That is. Okay. Similarly, for the other body also, you can see that there is an increase, but then and there is a drop, actually a sharper drop than the other one. But then after say 4 or maybe after about 4 or so, it tends to be constant. Okay, so that region where it tends to be constant is in the hypersonic range. And what it shows is that the CP. So now let's understand what's the practical implementation of it. Practical implication of it. Say if I'm able to do some experiments at say m equals 5, I for a given geometry, I conduct experiments at m equals 5. Then I have a pressure distribution, or I have a set of aerodynamic coefficients which I determine experimentally at Mach number 5. This shows that I can use those non-dimensional parameters, that is the CD values, even at higher Mach numbers, to be the same. Please remember, we are talking in terms of the non-dimensional parameters. So, for example, if I am talking about pressure, what I am saying here is being independent is not pressure. I am not saying that pressure is not a function of Mach number. This is not what I am saying. Okay, this is not what I am saying. What I am saying is that the non-dimensional pressure, that is P by rho v infinity squared, is independent of Mach number. So that's what I'm saying. That is, what is being independent of Mach number is not the absolute value of pressure, but it is the non-dimensional value of pressure, because when Mach number varies, the rho varies, and rho infinity varies, v infinity vary, rho infinity may vary, v infinity varies certainly, etc. So the ratio of P by rho infinity v infinity square is independent of Mach number. That's the conclusion that we draw from here. Similarly, CD, CL, etc. All are the non-dimensional parameters are independent of Mach number, which means that I can conduct experiments at lower Mach numbers, maybe 4, 5, etc., and assume the values to be constant. That is, when if my real application is Mach 10 or Mach 12 or Mach 15, I can still use the non-dimensional parameter to be. I can then scale it up using rho infinity, v infinity, etc. But the non-dimensionalist form, I can assume it to be constant. And that comes theoretically from the basis that we have seen, that is the non-dimensionalization of the equations, and it has been sort of confirmed experimentally also to a great extent for at least simple shapes like this. Okay, so this approach or this concept or this theory is what is known as Mach number independence in hypersonic flow. So just to summarize the implications of it, the test section Mach number, we can maintain it to a reasonable amount level in experiments and make the measurements and assume that these properties under inviscid adiabatic conditions, they can be constant over a significant range of Mach numbers. So we, instead of doing conducting experiments, which is very difficult, we'll see that soon, at higher Mach numbers, we can do experiments at lower Mach numbers and use the concept or the observation of independence, Mach number independence, to infer or to calculate values at higher Mach numbers. Now, if the question that comes out here is, we have not considered viscosity, we have not considered heat transfer. But in reality, in actual experimental, or rather in real applications of hypersonic flows, the impact of heat transfer, for example, will become very important. Because the flow velocity, when that is being brought down to near zero values near the surface, the dissipation of kinetic energy to thermal energy is very significant. So you have high temperatures. So because of high temperature gradient, you will have heat transfer. So those will have additional issues. But then in our analysis so far, we have not considered, we have not attempted to solve for heat transfer. We'll be doing that later, but here we are sort of considering only conditions in the adiabatic regime of flow, or rather subject to adiabatic conditions. Okay, any questions so far, please? Okay, now so something related to this, actually, when I say numerical problem here, this is not an application of Mach number independence, but this is in the context of what we are discussing here. That is about doing experiments in hypersonic flow, just to indicate some of the issues related to that. Okay, so that's what the purpose of using this numerical problem here is to highlight, because we are talking about Mach number independence, which is used to replace experiments or to whatever possible extent at higher Mach numbers. So what I am trying to hint, or what I am trying to show by this numerical problem is some of the limitations of hypersonic experimental facilities. Now, what is given here is the storage and supply for a Mach number 10 blow down wind tunnel. I'll explain what it is to be designed. Operating atmospheric conditions of are 300 Kelvin. That is, the static temperature is 300 Kelvin. And what is to be checked here is whether this will require preheating. What do you mean by preheating? That is, air need to be heated before it goes to the test section. That is to be tested, checked here. Now, in what case will you need to heat the air? Say, suppose that during the experiment, if the air temperature is going to be coming down before the liquefaction, air, then you have to condensed. So it is stated here is that examine whether this will require preheating before test section, liquefaction of air, and it is also mentioned that air starts liquefying at about 80 Kelvin under atmospheric conditions. So when if air comes below 80 Kelvin, it may start becoming the condensation may set in, which means that when you are actually doing an experiment, you don't want air to condense. You want it to be gaseous phase itself. Okay. So if you are doing an experiment, you should make sure that at no point in the test section, air temperature comes below 80 Kelvin, which means that you may have to heat it. That is what is being checked here, whether you need heating. Now, compare. Okay. Now, that second part is we'll look at it separately. But let's first check at the need for reheating air. Air is being air is issuing at 300 Kelvin. Section is supposed to have a. Okay. Now, before we actually solve it out, I'll just explain you what a wind tunnel looks like. You would have certainly seen the wind tunnel in the lab, but that is a subsonic wind tunnel. A supersonic wind tunnel may have almost similar components, but it's much more complex because of the need to have supersonic flow in the test section. And here we are talking about hypersonic flow, so it is even more complex. Okay. Certainly, it should have a high pressure storage. So you will have a tank, a huge tank. So it need not be circular. It need not be spherical as shown here, but in many cases it is spherical. I don't. Any of you visit? Had a visit to NAL Bangalore. They have a huge wind tunnel, which has a huge pressure tank, which actually is it looks as tall as a two-storied building or so. So it's quite common with such facilities to have huge spherical winter storage. Anyway, so that is an air tank. This is air tank, a storage vessel, air tank. And then, of course, you will have valves, etc., to control the pressure. You will have a straightening, settling chamber, and then you will have the test section. Obviously, before the test section, you need to have a CD nozzle to accelerate the flow to hypersonic velocity. To supersonic velocity. Since we are talking about hypersonic flow, it has to be accelerated to hypersonic velocity. And then you have the test section, and subsequently discharges into a low pressure chamber. So this is typically how the wind tunnel looks like. In fact, this is not the first time that you are being introduced to wind tunnel. In compressible flows, when we were discussing about CD nozzles in the compressible flow course, we have discussed about wind tunnels briefly. We have also discussed about why do we need a second throat, and what is the role of the stagnation pressure, or rather the control over the stagnation pressure by having a different throat here, etc. Anyway, so what we just recall that it need to have a supply, high pressure supplier, a supply tank. Will have a test section, and you will have a discharge section. Now, so when we talk about liquefaction, etc., what we are saying is that the air in this section should not come to be below liquefaction temperature. And when we say whether it requires preheating, what we mean is that either in the tank or in the settling chamber, should we need to heat the air? So that's a question. That's the context of the question. Now let's go back to the problem. So the question is whether it will require preheating before the test section. So I guess it's quite straightforward to calculate it. We know that the atmospheric temperature T0 is 300 Kelvin. I guess when I read the problem by mistake, I said static temperature. It's not static temperature. It's actually the stagnation temperature also here, because we are talking about a stagnant atmosphere. So here static, the value that you have in the atmosphere is equivalent to the stagnation temperature. The test section over so the tank is supplying at 300 Kelvin. Okay, and it is connected to a magnet. Now the question is, what is the static temperature at the test section? We can assume T0 to be constant everywhere. Stagnation temperature can be assumed to be constant. But the question here is, what is the static temperature? Because liquefaction depends on the static temperature. So now, if T0 is 300 Kelvin and Mach number is 10, we find what is T, right? It has to be T0 by 1 plus gamma minus 1 by 2 m square. Assuming adiabatic reversible adiabatic flow in between 1 plus gamma minus 1 by 2. So m squared is 100, right? Because m is 10. This m squared is as low as, you can check the calculation, 1.4. That's really low value, right? The 40.3 Kelvin is very, and particularly since air liquefies at 80 Kelvin, it means that invariably at fan is without preheating, which means that you cannot operate this facility with T0 is equal to 300 Kelvin. So you may have to heat it to, maybe, I don't know, I've not calculated it, but you may have to heat it to say something like 900, 1000 or 1100 Kelvin prior to taking it to the test section. So usually such facilities will have a preheater also, air preheater also, if the facility has to handle such high Mach numbers. So that's one issue related with them. That actually adds to the complexity of the test facility, to the need for having a preheating. Okay. Now the next question, or the continuation of the question, is compare stagnation temperature of this facility with that of flow around X43 at Mach 10. X43, the scramjet powered space vehicle, the conceptual one, or rather the research stage which is going on. So X43 at Mach 10 at an altitude of 20 kilometers. So with all this difficulty, if I am doing an experiment, am I able to model the stagnation temperature that would be exposed to X43 at Mach 10? Then I can calculate it. Say because altitude is given as 20 kilometers, which means that Mach number, sorry, the static temperature you can take as something like what, 216, 215, 16, that range, or maybe slightly lower than that. So static temperature you can take, and Mach number is given as 10. So you can calculate the stagnation temperature, and that comes to be. So in real operation of this scramjet engine, scramjet powered vehicle, comes to be something like 4,411 Kelvin. 4,411 Kelvin. Okay. Whereas the experimental facility operates only at 300 Kelvin. If you are not, and even if you than that. So this full of an X43 of a vehicle that is powered by an X43. Okay, so this I'm highlighting these numbers. I'm bringing down this comparison here in order to drive home the point that hypersonic flows, doing experience in hypersonic flows, reproducing hypersonic conditions is quite complex. So many times the kind of equivalence that you draw from lower values theoretically to a higher Mach numbers can give an useful initial estimates for hypersonic conditions. Okay, is that clear? Should we discuss any of these points further? Okay, if not questions, we'll stop here for the day. I would request you all to upload the assignments today, so that tomorrow I would request them to be presented. Okay, so each team should be ready with maybe a slide or so with the results as well as their the observations that you make. Tomorrow we'll spare some time for the presentation. So I request everybody to have the second assignment to be uploaded today. Okay, so for today we stop here. If you don't have any questions, thank you and bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks.